Lecture 1. The Atom. Protons, Neutrons, and Electrons. Let's begin with the basic structure of the atom. An atom is the smallest unit of an element that still keeps the chemical properties of that element. At the center of the atom, there is a nucleus. The nucleus contains protons and neutrons. Protons have a positive charge. Neutrons have no charge. Electrons have a negative charge, and they occupy energy levels around the nucleus. In a neutral atom, the number of protons is equal to the number of electrons. This is important because protons identify the element, but electrons determine many chemical properties. So even though most of the mass is in the nucleus, chemistry is often controlled by the behavior of electrons. Lecture 2. Atomic number, mass number, and isotopes. Now let's connect this to atomic number, mass number, and isotopes. The atomic number is the number of protons in an atom. This number identifies the element. For example, any atom with 17 protons is chlorine. The mass number is the total number of protons and neutrons. So if chlorine has a mass number of 37 and chlorine has 17 protons, then it must have 20 neutrons. Atoms of the same element can have different numbers of neutrons. These are called isotopes. So chlorine 35 and chlorine 37 are both chlorine because they both have 17 protons. But they are different isotopes because they have different numbers of neutrons. The key idea is this. Same number of protons means same element. Different number of neutrons means different isotope. Lecture 3. Rutherford gold foil experiment. Next, let's look at Rutherford's gold foil experiment. Rutherford fired positively charged alpha particles at a very thin sheet of gold foil. Most of the alpha particles passed straight through. Some particles were deflected, and a very small number bounced back. This result was surprising. If the atom were a solid sphere, many more particles would have bounced back. But most particles passed through, which showed that atoms are mostly empty space. The few particles that bounced back showed that positive charge and mass are concentrated in a very small, dense center. That center is the nucleus. So Rutherford's experiment showed that the atom has a small, dense, positively charged nucleus, and that most of the atom is empty space. Lecture 4. Coulomb's law, charge and distance. Now we move to Coulomb's law. Coulomb's law explains the force between charged particles. The electrostatic force depends on charge and distance. If the charges are larger, the force is stronger. If the distance is shorter, the force is stronger. Opposite charges attract, like charges repel. This matters in chemistry because electrons are negatively charged and the nucleus is positively charged. So electrons are attracted to the nucleus. When the nucleus attracts electrons more strongly, electrons are held more tightly. When the attraction is weaker, electrons are easier to remove. This idea helps explain atomic radius, ionization energy, and many periodic trends. Lecture 5. Shielding and effective nuclear charge. Now let's talk about shielding and effective nuclear charge. Electrons do not all feel the full pull of the nucleus. Inner electrons are closer to the nucleus. Outer electrons are farther away. The inner electrons can block some of the attraction between the nucleus and the outer electrons. This is called shielding. Because of shielding, the outer electrons feel a reduced nuclear pull. That reduced pull is called effective nuclear charge. If shielding increases, the outer electrons feel a weaker attraction. If effective nuclear charge increases, the outer electrons feel a stronger attraction. This is one of the most important ideas in AP Chemistry Unit 1. It helps explain why atoms get smaller across a period and why ionization energy changes across the periodic table. Lecture 6. Energy levels and subshells. Now let's look at energy levels and subshells. Electrons occupy energy levels around the nucleus. These energy levels are labeled with numbers such as n equals 1, n equals 2, n equals 3, and n equals 4. Inside each energy level, there are subshells. The main subshells are S, P, D, and F. The S subshell can hold 2 electrons. The P subshell can hold 6 electrons. The D subshell can hold 10 electrons. The F subshell can hold 14 electrons. The 1s subshell is the lowest energy subshell. As energy increases, electrons occupy higher energy levels and higher energy subshells. This structure helps us write electron configurations. Lecture 7. Aufbau principle and orbital filling. Now let's use the Aufbau principle. The Aufbau principle says that electrons fill lower energy orbitals first. So when we write an electron configuration, we do not place electrons randomly. We follow the order of increasing energy. For a neutral atom, the number of electrons is equal to the atomic number. Take fluorine as an example. Fluorine has atomic number 9. So a neutral fluorine atom has 9 electrons. The electron configuration is 1s2, 2s2, 2p5. This means 2 electrons are in the 1s subshell, 2 electrons are in the 2s subshell, and 5 electrons are in the 2p subshell. The key idea is simple. Use the atomic number to count electrons. Then fill the lowest energy orbitals first. Lecture 8. Full and condensed electron configuration. Next, let's compare full and condensed electron configurations. A full electron configuration lists all the electrons. For example, oxygen has atomic number 8. So oxygen has 8 electrons. The full electron configuration is 1s2, 2s2, 2p4. But we can also write a shorter version. This is called the condensed electron configuration. The condensed version uses the symbol of the previous noble gas to represent the inner electrons. For oxygen, the previous noble gas is helium. So the condensed configuration is helium in brackets, followed by 2s2, 2p4. Both versions mean the same thing. The full version shows every electron. The condensed version is shorter and focuses more on the outer electrons. Lecture 9. Photoelectron Spectroscopy. Now let's move to Photoelectron Spectroscopy, often called PES. PES gives experimental evidence for electron structure. In a PES spectrum, each peak represents electrons in a subshell. The binding energy tells us how strongly the electrons are held. Higher binding energy means the electrons are closer to the nucleus and more strongly attracted. Lower binding energy means the electrons are farther from the nucleus and less strongly attracted. The height or area of a peak shows the relative number of electrons in that subshell. So PES connects electron configuration to real experimental data. It helps us see where electrons are located and how strongly they are held. Lecture 10. Identifying an element from a PES spectrum. Now let's identify an element from a PES spectrum. If the spectrum shows 2 electrons in 1s, 2 electrons in 2p, C, and 2 electrons in 2p, then the total number of electrons is 6. For a neutral atom, the number of electrons equals the number of protons. So this atom has 6 protons. An element with atomic number 6 is carbon. Therefore, the element is carbon. Its electron configuration is 1s2, 2s2, 2p2. This is why PES is powerful. It lets us connect peaks on a graph to electron configuration and then to the identity of the element. Lecture 11. The mole and Avogadro's number. Now let's move from atoms to the mole. Chemists need a way to count extremely tiny particles. We cannot count atoms one by one in the laboratory, so we use the mole. A mole is a counting unit. 1 mole always contains 6.022 times 10 to the 23rd particles. This number is called Avogadro's number. The word particles can mean different things. For an element like copper, the particles are atoms. For water, the particles are molecules. For sodium chloride, the particles are formula units. For ions, the particles are ions. So the mole is a bridge between the microscopic world of particles and the measurable world of grams. Lecture 12. From mass to moles to particles. In chemistry, we often need to convert between grams, moles, and particles. These 3 ideas are connected, but they do not mean the same thing. Grams tell us the mass of a substance. Moles tell us the amount of substance. Particles tell us how many atoms, molecules, or ions we have. The key idea is this. If we start with grams, we first convert grams into moles using molar mass. Molar mass is the mass of 1 mole of a substance. So the formula is moles equals mass divided by molar mass. After we know the number of moles, we can convert moles into particles using Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd. That means 1 mole contains 6.022 times 10 to the 23rd particles. Let's look at the example. We are converting 18.0 grams of H2O into molecules. First, we find the molar mass of water. Hydrogen has a molar mass of about 1 gram per mole, and oxygen has a molar mass of about 16 grams per mole. Since water has 2 hydrogen atoms and 1 oxygen atom, the molar mass is 18 grams per mole. Now we convert grams to moles. 18.0 grams divided by 18 grams per mole gives 1.00 mole of H2O. Now we convert moles to molecules. 1.00 mole times Avogadro's number gives 6.022 times 10 to the 23rd molecules of H2O. So the final answer is 6.022 times 10 to the 23rd molecules. The order is very important. Use molar mass first, then use Avogadro's number. Grams to moles, then moles to particles. That is the main conversion pathway. Lecture 13. Mass spectrum and average atomic mass. A mass spectrum helps us see the isotopes of an element. Each peak in a mass spectrum represents an isotope. The position of the peak tells us the mass to charge ratio, which is often very close to the mass number for singly charged ions. The height of the peak tells us the relative abundance of that isotope. In this example, we are looking at chlorine. Chlorine has 2 main isotopes, chlorine-35 and chlorine-37. The mass spectrum shows that chlorine-35 has a relative abundance of 75.8%. Chlorine-37 has a relative abundance of 24.2%. This means chlorine-35 is much more common in nature than chlorine-37. Now let's use this information to calculate the average atomic mass. Average atomic mass is a weighted average. That means we do not just add 35 and 37 and divide by 2. We must include the abundance of each isotope. So we multiply the mass of each isotope by its decimal abundance. For chlorine-35, we do 35 times 0.758. For chlorine-37, we do 37 times 0.242. Then we add those two values together. This gives approximately 35.5 atomic mass units. That is why the atomic mass of chlorine on the periodic table is about 35.5, not exactly 35 or 37. The key idea is simple. Average atomic mass depends on both isotope mass and isotope abundance. The more abundant isotope has a bigger effect on the final average. Lecture 14. Moles of molecules versus moles of atoms. This part is very important because students often confuse moles of molecules with moles of atoms. A mole of a compound refers to the particles shown by the chemical formula. For molecular compounds, that usually means molecules. For example, 1 mole of H2O means 1 mole of water molecules. That is 6.022 times 10 to the 23rd water molecules. But 1 water molecule contains more than 1 atom. The formula H2O tells us that each water molecule contains 2 hydrogen atoms and 1 oxygen atom. So if we have 1 mole of H2O molecules, we have 2 moles of hydrogen atoms. And we also have 1 mole of oxygen atoms. This is where the subscripts matter. The subscript 2 after hydrogen means there are 2 hydrogen atoms in each water molecule. The oxygen has no written subscript, so we understand it as 1 oxygen atom. Now let's connect this to Avogadro's number. 1 mole of H2O molecules contains 6.022 times 10 to the 23rd water molecules. But because each molecule contains 2 hydrogen atoms, that same sample contains 2 times 6.022 times 10 to the 23rd hydrogen atoms. And because each molecule contains 1 oxygen atom, it contains 1 times 6.022 times 10 to the 23rd oxygen atoms. So remember this clearly. 1 mole of molecules does not always mean 1 mole of atoms. Always read the formula carefully. Use the subscripts to count how many atoms of each element are present. Lecture 15. Pure substances and mixtures. Matter can be classified as pure substances or mixtures. A pure substance has a fixed composition. This means the substance always has the same type of particles in the same ratio. There are 2 main types of pure substances, elements and compounds. An element contains only 1 type of atom. For example, if every particle is the same kind of atom, then the substance is an element. A compound contains 2 or more different elements chemically bonded together in a fixed ratio. Water is a compound because hydrogen and oxygen are chemically bonded in a fixed ratio. Now let's compare this with mixtures. A mixture has a variable composition. This means the amounts of each substance can change. The substances in a mixture are not chemically bonded in a fixed ratio. Mixtures can be homogeneous or heterogeneous. A homogeneous mixture has Lecture 16. Molecular compounds versus ionic compounds. Now let's compare molecular compounds and ionic compounds. These two types of compounds may both contain more than one element, but the way their particles are held together is very different. Molecular compounds are made of molecules. A molecule is a small, separate group of atoms that are covalently bonded together. Covalent bonding means the atoms share electrons. For example, water, H2O, is a molecular compound. Carbon dioxide, CO2, is also a molecular compound. In these compounds, the atoms are connected by shared electrons, and the compound exists as individual molecules. So when we talk about molecular compounds, we usually think about discrete molecules. That means each molecule is its own separate unit. Now let's compare that with ionic compounds. Ionic compounds do not usually exist as separate molecules. Instead, they form repeating lattice structures. A lattice is a regular, repeating arrangement of positive and negative ions. For example, sodium chloride, NaCl, is an ionic compound. Sodium transfers an electron to chlorine. Sodium becomes a positive ion, and chlorine becomes a negative ion. These oppositely charged ions attract each other and form a giant repeating lattice. That is why we say ionic compounds exist as formula units, not molecules. A formula unit is the simplest ratio of ions in an ionic compound. For NaCl, the ratio is 1 sodium ion to 1 chloride ion. For magnesium oxide, MgO, the ratio is 1 magnesium ion to 1 oxide ion. For calcium fluoride, Kf2, the ratio is 1 calcium ion to 2 fluoride ions. So the key difference is this. Molecular compounds form molecules because electrons are shared. Ionic compounds form repeating lattices because electrons are transferred and ions attract each other. Molecular compounds have discrete molecules. Ionic compounds have formula units in a lattice. Lecture 17. Empirical formula versus molecular formula. Now let's look at empirical formulas and molecular formulas. These two formulas are related, but they do not show exactly the same information. An empirical formula gives the simplest whole number ratio of atoms in a compound. A molecular formula gives the actual number of each type of atom in one molecule. Let's use glucose as the example. The molecular formula of glucose is C6H12O6. This tells us that one molecule of glucose contains 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So the actual composition is 6 carbon, 12 hydrogen, and 6 oxygen. But the empirical formula is simpler. If we reduce the ratio 6 to 12 to 6, we can divide every number by 6. 6 divided by 6 is 1. 12 divided by 6 is 2. And 6 divided by 6 is 1. So the simplest ratio is 1 carbon, 2 hydrogen, and 1 oxygen. That gives the empirical formula CH2O. So for glucose, the molecular formula is C6H12O6, but the empirical formula is CH2O. The relationship is also important. The molecular formula is a whole number multiple of the empirical formula. In this case, CH2O multiplied by 6 gives C6H12O6. So when you see an empirical formula, remember that it does not always show the actual number of atoms in the molecule. It only shows the simplest ratio. The molecular formula shows the real number of atoms in one molecule. This is especially important in chemistry problems. Two different compounds can have the same empirical formula but different molecular formulas. For example, a compound with CH2O could be 1 unit of that ratio, or it could be 6 units of that ratio, like glucose. So the key idea is this. Empirical formula means simplest ratio. Molecular formula means actual composition. And you can convert between them using a whole number multiple. Lecture 18. Periodic trends, atomic radius, and ionization energy. Now let's look at two important periodic trends, atomic radius and ionization energy. Atomic radius means the size of an atom. Ionization energy means the energy needed to remove an electron from an atom. These two trends usually move in opposite directions. Let's start with atomic radius. Atomic radius increases as you move down a group. This happens because atoms gain additional electron shells. More electron shells mean the outer electrons are farther away from the nucleus. So the atom becomes larger. Atomic radius also increases as you move to the left across a period. This means atomic radius generally decreases from left to right. Why does it decrease from left to right? Across a period, the number of protons increases. This increases the effective nuclear charge. Effective nuclear charge means the attraction felt by the outer electrons from the nucleus. As the nuclear charge gets stronger, the electrons are pulled closer to the nucleus, so the atomic radius becomes smaller. Now let's look at ionization energy. Ionization energy increases as you move up a group. It also increases as you move to the right across a period. Across a period, effective nuclear charge increases. The nucleus pulls the electrons more strongly, so it becomes harder to remove an electron. That means ionization energy increases. Down a group, ionization energy decreases. This happens because there are more electron shells. The outer electron is farther away from the nucleus. There is also more shielding from inner electrons. Because of this shielding, the outer electron feels less attraction from the nucleus, so it is easier to remove the electron. That means ionization energy is lower. Now compare the two trends. Atomic radius increases down and to the left. Ionization energy increases up and to the right. The reason is based on two main ideas: effective nuclear charge and shielding. Across a period, effective nuclear charge is the main factor. The nucleus pulls electrons more strongly, so atomic radius decreases and ionization energy increases. Down a group, shielding is the main factor. More electron shells make the outer electrons farther from the nucleus, so atomic radius increases and ionization energy decreases. So remember the final rule. Effective nuclear charge explains trends across a period. Shielding explains trends down a group. Atomic radius gets larger down and left. Ionization energy gets larger up and right.